So this solution, you see, I have it here. One-page paper. This is the best published paper in the history of physics. Just one page. Because he discovered this psi2 complex represents rotating black holes. So, as I said, this Roy Kerr, he did not do much things after this because this was enough to make him famous. In most of the books, you can see a nice picture of him. So they put the picture of Schwarzschild and a picture of Kerr. So Kerr was from New Zealand. He is a New Zealander. In fact, New Zealand has an interesting history. Rutherford also was from New Zealand. And nowadays, there is also one very brilliant man, Matt Visser. Matt Visser also, he is working in New Zealand and he is doing amazing things. And the recent works, I searched if there are some people working on the polarization properties of gravitational waves. The most recent study that I found was Visser. Visser started to get interested in the polarization of gravitational waves. So he published some papers, but I don't know whether he published these because I could not see anything new in these works, aside of what I had done some 25 years ago. But it is good that he brought the subject again under focus, so it may attract attention again, so that maybe there will be more people to get interested in the gravitational waves, their polarization properties, and so on. So, now in general, these objects, these polarization properties of these 5 complex functions can be determined as follows. Now, from our electromagnetic analogy, you know, how do you know whether an electromagnetic wave passes from here or not? What do? You put some charged particles, and if an electromagnetic wave passes, because electromagnetic wave is transverse, you will see that the charged particles will be pushed or pulled. So you will say, ah, there is an electromagnetic wave passing in the z direction. So it has transverse effect in the x and y direction. So this is how we can know about whether an electromagnetic pass or not, because we do not see. You know, in the air, there are electromagnetic waves. If there was no, how is it that your mobile works? How is it that your television works? They work by all electromagnetic waves, but we do not see them because they don't address our eyes, they address our minds. We have to find a way to understand what is the electromagnetic phenomena. So thanks to Maxwell and the others. So now the polarization of gravitational waves. I think the best and the simplest characterization is and the way to discover the property of the polarization, because polarization is related to the spin property of the wave. They are related. Now, one of the most interesting aspect about polarization is that some serious physicists, they think that polarization property is a tachyonic property. That means it travels faster than the speed of light. But this has never been proved. Because as an example, we can talk about the EPR paradox. EPR, this is the most famous paradox in the history of physics. Effect here transmits instantly to light years away. This is the EPR paradox. How can this be? That means that the connection between the two items, it can be photons, a pair of photons. So the transmission speed of that connection may exceed the speed of light. But this, as I said, has never been proved. So a scientific proof can only be by deriving a wave equation for the polarization vector that satisfies for a faster than speed of light equation. We know what is a wave equation, which moves at the speed of light, but here it must be more than the speed of light. So this is one of the interesting property of the polarization property, even for electromagnetic waves, not only for gravitation. So it can be a tachyonic, faster than the speed of light property. That question is still open, so I have no proof in my hand. And those functions that I have cited over there, now under a passage of a gravitational wave, they behave differently. Because, in fact, this one and this one are spin one part of gravity. This is also spin one. This one spin two part. And, sorry, this should be spin two, this should be spin one. That means spin one. That means this and this behaves like electromagnetic waves. These psi 4 and psi 0 behaves differently. They are true gravitational waves because they carry spin 2. How do I prove this? In order to prove this, I have to make a coordinate transformation and see under a rotation, I will see that psi 2 prime will remain same because it is scalar, spin 0 part. So this is spin 0, but psi 4 prime, it will be 2i phi psi 4. So now it will pick a factor, and the other one, psi 1 and psi 3, will pick a factor of I phi, I phi psi 1. So these transformation properties tell me what is the spin that it carries. Because in physics there is a principle. If a rotation by pi over s brings you to the same polarization state, the spin of that wave is s. So this is well known. In spinors, s is 1/2. So you have to make 4 pi rotation. 2 pi rotation does not bring you to the initial. And so accordingly, this psi 4, if I make a 90-degree rotation, it brings me to the same point. So that is the reason that it picks 2 factor, 2 phi. You have to make pi over 2 rotation. This you have to make pi rotation. So this is how you decide about the polarization and the spin properties of these waves. So all the calculations I have done very simply. When we were doing a work on in 2007, we had done a work similar. What was it? In here, we wanted to see what happens if you have an electromagnetic wave coming, and from the other side you have a gravitational wave. So they make collision. What happens after? So the difficulty here is that you can never observe this. This is like ghost. But this one you can observe. So how they detect ghosts? You know, today there are some old houses, old hotels, that some people may search to see whether there are ghosts or not. Because ghosts do not interact with normal matter. So how do we find it out? We are facing the same problem here. You cannot detect gravitation, but you study the electromagnetic wave when it just makes a collision in interaction with the gravitational wave. By calculation, I can find out what changes there will be on the electromagnetic wave after it encounters a gravitational wave. So we saw that all there. Okay. So therefore, what we said in that paper, if the electromagnetic wave, before it encounters a gravitational wave, has these properties, after the encounter, it will have these new properties. So, what is that property? You know what we have chosen? It is a very simple physics problem. Just consider that you have two sticks. They are coming face to face, and they make a collision. Okay? So they get depart. This is just simple momentum conservation. We do it with balls in general, but when you are dealing with waves, these waves have fronts, so it is not only particle-like, but they are like front-like. Like you can imagine a surface, another surface, so they come and hit each other, and then after that they depart. What changes you observe in the electromagnetic wave will give you information about the gravitational field. Okay? So this is the method that they have announced 3 days ago about the discovery of gravitational wave, which I know for the last 40 years. But there are some tricks here. If you consider linearly polarized electromagnetic wave, linearly polarized gravitational wave, they hit, you do not have much observable effects. So you want to catch something that you get by the effect of gravitational wave. So our trick here was, what we did, we rotated the gravitational wave. We gave it a rotation. And now when the electromagnetic wave came with linearly polarized, because there was a rotation on the gravity, after it hits it, the electromagnetic waves gain rotation. So automatically it admits a second polarization. That means the rotational mode of the electromagnetic wave. Before the encountering gravitational wave, it was linearly polarized. It had only 1 degree of freedom, but we are using a rotated gravitational wave. Hitting the gravitational wave is like hitting the wall. It is a very strong object. So after that, partly it reflects, partly it diffuses. and you study the changes there, okay? So the most important effect that we had observed was the rotational effect of the gravitation, electromagnetic wave. That means as a result of that encounter, electromagnetic wave gains rotation. This was our, effectively our conclusion. So we said ourselves, if you observe this rotation in an electromagnetic wave in this space, you can judge that, this electromagnetic wave crossed a gravitational wave. So that means there is gravitational wave. You see, indirectly, you can judge about the existence of the electromagnetic gravitational waves. So this was our conclusion in 2007, and this was the conclusion 3 days ago that they announced. If that announcement is correct, I think they will get Nobel Prize. They will get Nobel Prize. And I will get a cup of water. Because my work is all theoretical. You see, when you are dealing with theory, then who cares about your work? Well, you thought like this or like that. Now, but I have a question now to those people who have announced this experiment. From my past experience of these 2 papers, how do they know that the electromagnetic wave encountered a gravitational wave? Because my calculation shows that if an electromagnetic wave encounters a double polarized electromagnetic wave, it shows the same effect. They have to answer that. You see? Because I have theoretical calculations that if you consider 2 electromagnetic waves that they have, now I said this is linearly polarized. Now I rotate them, both electromagnetic, and I make them to interact. After the interaction, automatically my electromagnetic waves will start to rotate, and they will give rise to the B mode, rotating mode, cross-polarization mode, or it has also some more names that different authors use different things. But shortly they call it the second mode, or so you need 2 parameters to specify a gravitational wave. Why? Because it is spin 2 field. You need 2 independent parameters to characterize. So in electromagnetic wave, 1 is enough, okay? But in the case of when you are using that mode also for gravitation, that is spin 2, and it gives effect to rotational effect on the electromagnetic wave. So this is the summary of what they have found in recent last 3-4 days. So we are excited. We want to see that it is correct, because the experiment is very, very sophisticated. They took their setups to Antarctica so that they are free from any environmental effects. Okay? So you have to get rid of all noises. So this is a very, very sensitive experiment. I think in 1968, also it was announced that someone by the name Joe Weber, he was making experiments at the University of Maryland, United States. All of a sudden, he saw that his cylindrical detector detected some vibrations. that he was expecting was gravitational waves.